Hello, Elizabeth ma'am. Good morning.
Good
I'm
morning. Good
Prajof.
morning.
Yeah.
Yeah,
Please do let me know when I need to begin.
yeah, sure. I'll be starting now. Okay.
Yeah.
Okay. Okay. A very good morning to all our participants from the Department of EEE RSET. I wish you all Bakrid Mubarak to all, and may this festival of sacrifice and faith bless your journey with good health for you and your family, especially during this pandemic. And I'm happy to see that even though it's a public holiday, we have participants joining in. Thank you. Uh, and today we have with us Dr. Prajof Prabhagan. He is Assistant Professor of NIT Suratkal. He was awarded his doctoral degree from IIT Mumbai. His expertise lies in the power electronics, electric drives, and mathematical modeling. Prior to his affiliation with NIT Suratkal, he was working as project lead with L&T, and his works were mainly related to the R&D aspects of battery management system, EV chargers, and powertrain. He also has several papers in referred journals and conferences. Dr. Prajof, I invite you for the session.
Yeah. Thank you so much, ma'am, for the introduction. I hope I'm audible.
Yes, sir.
Yeah. Okay. Yeah. So good morning, one and all. So happy Eid to one and all. Yeah. So before I begin, I would like to thank Dr. Elizabeth for inviting me for this FDP. I would also like to thank the other faculty members of the Department of Electrical and Electronic Engineering and the management of Rajagiri School of Engineering for this FDP and for inviting me. Thank you so much. Okay, so before I begin, I think I would also take the poll which Professor Venkata madam took it. So I would request you all to maybe log into menti.com, which I have, maybe I'll post it in the chat. Just to I've just posted in the chat. So this is just to take the feedback. You'll be asked a code. Please do type 4960 and 50. Yeah, so the participants, you can just type menti.com, which I have typed it in the chat, menti.com. I'll just try sharing that. Yes, you can just keep, you need not close the screen. You can just keep it on. I'll pose the next question in a few minutes. Yeah, I think there are now around close to 15 who have responded. Okay, I'll just wait for another 30 seconds before moving to the next slide, just to get a feedback of the, just to see just the flavor of the audience. Okay, I can see in the, as you can see in the screen, most of you are not from the power electronics background. All right, I'll move to the next question. You can still continue to be in that site, or if you have logged it out, you can again log into the, and please do answer the next question. So I have, you are faculty, PhD research scholar, or both, or others. Okay, so I think I've got a fairly good idea. So yeah, thank you so much for this. So I think most of you are not from power electronics background, and most of you are faculty. Okay, thank you so much. Now I'll just share my slides. Just a minute. Yeah, I hope my slides are visible. I'll just make it.
Yes, Dr. Prajof.
Yeah, thank you so much. Yeah, okay. So those who have joined late, I'm Prajof. I'm currently working as an assistant professor in NIT Suratkal. I have completed my PhD from IIT Bombay. My PhD research was on DC microgrid systems. And post my PhD, I have worked briefly at NIT Calicut as an ad hoc faculty, and then went on to work in L&T Bangalore as an R&D engineer in the field of EV powertrain and battery management systems. So I'm basically a power electronic person. I have my MTech degree in power electronics. So I'm not a core power electronic person, as I could see from the other speakers. But I have definitely used control systems in building various power electronic systems. I have worked on various government projects when I was in IIT. I've also worked on some of the industrial projects like building a EV charger and UPS systems, where I have used these control application into power electronics. So what I would be explaining in these slides would be my experience in implementing control systems in power electronic applications. Okay, so this will be the outline of my presentation, where I would discuss three important aspects. The first, starting with the introduction, the control of DC-DC converters. I shall go a little bit into detail, where I would discuss about the modeling methods. I'll take an example of a buck-up boost converter. I'll discuss a compensator design that we use called K-factor approach. And we'll see the voltage and current control of DC-DC converters, also called as switch mode power supplies. I'll just throw a light on digital implementations, and I'll also see some of the applications. Then I'll go ahead and discuss control of DC-AC converters, or also called as inverters. Okay, introduction. So before I go into the detailed aspects of the control of power electronic systems, I would like to give a brief introduction to power electronics, as most of you are from non-power electronics background. So this is the definition as seen. This is the definition given by the late Professor Neville, who was a well-known professor, one of the early professors working in the field of power electronics. In fact, there is an IEEE award named after Professor Neville. So according to him, power electronics basically deals with the use of electronics for the control and conversion of large amount of electric power. So that basically puts it, which basically says a power converter basically converts a large amount of power, which is as suitable by the load or the user. Now, power electronics basically encompasses three main domains: the power, the electronics, and the control. So if you see, power electronics is actually a subset of all the three. So if you look at any power electronic converter systems, this is a block diagram of a power electronic converter systems. You would have the input port, you would have the output port, and the control or feedback part, where you are trying to go and regulate the electrical output. Okay. So you can have input of one nature and output of a different type of nature. So based on that, the power converters are classified into these categories, which are DC-DC, DC-AC, AC to DC converter, and AC to AC converter. In this lecture, I would try to focus on the first two parts, the control of the first two parts, that is control of DC-DC converter and control of DC to AC converters. Okay, this is just to show the highlights of the power applications of power electronics. As most of you are from electrical and electronics background, you would have realized the importance of power electronics. It is used in almost all the fields, starting from the automation and traction systems. You have the modern electric vehicles, the traction systems, all utilizing power electronics. Even the future technology, like more electric aircraft and more ships, where it is anticipated that the hydraulic and pneumatic systems would be replaced by power electronics or electrical systems. Even in our day-to-day life, we have UPS, consumer electronic loads. Most of the consumer electronic loads, we have power electronics. If you see, in fact, today, most of the loads, they use power electronics. Even the conventional loads, like refrigerator and air conditioning, they come with inverter grade. So they have power electronics. Even the other applications, including renewable energy, in power systems, and in industries like heating and cooling, motor drives, constructions, we have power electronics. So this is just to give some highlights into the importance of power electronics. Okay, now moving ahead to the power electronics control, target, and configurations. See, the performance of power electronics depends on two aspects. I have understood this from my experience. One thing, it depends on the hardware design, no doubt in that. For ensuring good reliability and robustness of the converter or any power converter, hardware design is quite critical. Okay, but more than that, even if you design the hardware very perfectly, there's no point. I mean, the performance would be, if the control strategy is not designed well, then there is no point in putting that much effort in the hardware design. So control strategy and the controller design is also equally important to ensure good performance of power converter. In fact, if I would say the hardware is actually a muscle for power electronic systems, and control is actually the base, the brain for the power electronic systems. So that's the importance of the control and controller design. Now, if I look into the power electronic control targets, what is the requirement from the power electronic control? Well, these are some of the following requirements which I've jotted down here. The first important requirement is high dynamic performance, because power electronic systems are mainly employed in some large systems like electric vehicles, grid connected like solar PV or wind systems, where the requirement is that the power electronic system should act quite fast. So you need quite high dynamic response, meaning that minimum overshoot and less settling time. That is one of the control targets for power electronic systems. And there should not be any phase or amplitude error in steady state. That's obvious, because there should not be any steady state error in terms of phase for AC systems and even in amplitude. There should also be reduced harmonic content. For example, if I have a DC-DC converter, then the output should be pure DC. It should not have any other components. Similarly, if it's a DC-AC converter, then the output should have only the fundamental component. It should not have any other component. But practically, that's not possible. This is the ideal requirement. Another thing to be noted is that the first and this point contradict each other. If you have high dynamic performance, you would try to have high harmonic content. And if I try, reducing the harmonic content, I might try to compromise the dynamic performance. So while designing the control for power electronic systems, we'll have to take care that we have a good trade-off between these 2 points. Also, we need to ensure that there is a good performance during load series parameters, during the voltage, due to the change in DC link voltage, and due to the change in the output voltage, or so all the even some unknown disturbances, the system must perform very well. So these are the control targets. Moving ahead, we'll see what are the control classifications of power electronic systems, where we can classify into different categories. What I have done here is I've classified it based on the 2 methods. One is control with modulator and control without modulator. Now we'll see what is the control with modulator. Here actually the controller has to track an average value of the converter output. It is actually provided in the form of a duty ratio. So this duty ratio, it needs to be, see, for power converter, we need to give switching pulses, because we have devices, electronic devices, which would operate based on some gating pulses. So here this duty ratio needs to be converted with some switching pulses, and that is done by a modulator. Okay. So which is generated through it is also called as PWM technique, which is called pulse width modulation technique. So where this duty ratio is converted to switching pulses. There are different PWM methods like sine pulse width modulation, space vector modulation, harmonic injected PWM, and so on. The merits with this type of control is that the switching frequency is fixed, so hardware design becomes quite easier, and we can apply the linear control theory. See, in power electronics, we can apply both linear as well as non-linear control, but in most of even in the industry, we mainly go with linear control, because with linear control, the job gets done. But nowadays, I do see that even in industry, people are going with some of the non-linear method to achieve a much better performance. Okay, and now with this control with modulator, the design of controller, for designing the controller, we need to use an average model of the converter, and the load is just normally used. Here, for the control purpose, the fundamental component and harmonic component are decoupled. So that needs to be taken care here. So while in the control purpose, we decouple the harmonic and fundamental part, and it is the fundamental part that goes into the control purpose, in the control loop. Okay, now if we look at the control without modulator, so here the gating signals are directly generated by the controller. So here the aim is to reduce the instantaneous error between the reference and the control variable. In the previous case, it was not the instantaneous, it was the average value. So the main merit is, since you are dealing with the instantaneous value, there is improvement, a significant improvement in the transient operation. Drawback is that there could be cases where the switching frequency is not constant. So there could be random behavior in switching frequency that makes the hardware design quite difficult. And that are some of the drawbacks. Now here, both fundamental and harmonic component are not decoupled. Unlike the previous case, it's not decoupled. And in this case, mostly the controller are of nonlinear type. For example, hysteresis, you have direct torque or direct power control, and model predictive control. So in all such cases, the controller itself tries to generate the switching pulses. Okay, so that was about the classification of power electronic control. So I'll just discuss two main converters. where my focus would be mainly on the linear control. I will not be discussing on the non-linear control, so I'll be mainly focusing on the linear control, mainly because it is a linear control that is being used mostly in practical applications. So starting with the control of DC-DC converters, which is also called switch mode power supplies. So what exactly is a DC-DC converter? It's basically a power supply which converts DC voltage of one level to DC voltage of another level. Yeah, you can have DC-DC conversions in other means. For example, you can also use the electronic devices in a linear region. It's also called linear mode supplies, or you can also have some sort of a potential divider. So there are basically three methods, but out of these three, switch mode power supplies are quite popular, mainly because it is more efficient and it is more compact. So that's where it is generally popular when the power levels are in the order of few hundreds of watts to few kilowatts. So there are two types of DC-DC converters. One is the non-isolated type, where there is no isolation, electrical isolation between the input port and the output port. Some of the examples are buck boost, Chuk, Sepik, Leo converters, and so on. There could also be other category, which is isolated converter, where there is an electrical isolation between the output port and the input port. This is achieved through some high frequency transformer. And some of the examples include flyback, forward, push-pull, dual active bridge, and so on. So this is just the block diagram which shows the control of a DC-DC converter. So this power stage, you would have the switches, the diodes, and passive elements like inductors and capacitors. So if you take any power electronic systems, you would basically find these elements. And here, for the control purpose, you need to have a sensor because you need to scale it down and maybe provide some sort of electrical isolation and give some reference to the controller. So here I would use controller, error amplifier, compensator interchangeably. That is how we power electronics people use. Whereas in industry, I find that controller and compensator are two different things. Controller is basically the embedded controller, which that is where we say controller, whereas compensator is the algorithm that is implemented. But right now for this presentation, controller and compensator I would use interchangeably. So this is the PWM generator generating the switching pulses. So here the main aim is to regulate the output to a desired value under all operating conditions. Now to design the controller, here for this, we need to model this power stage. Okay. So that is the requirement, because we need to model this and then we can design the controller. And that modeling method is called dynamic model. We use two methods for dynamic modeling. One is the state space and transfer function. I'll just discuss that more in detail in the coming slides. Okay, but one thing we need to take care is when we model, we should ensure that the model is very close to the actual converter. It demonstrates or it exhibits the behavior of the actual converter. So we need to take care of that while modeling. Okay, so this is the same thing, control diagram put in a control block diagram, in a block diagram form. So here, unlike the other systems, there are some challenges involved, especially in power electronics, because in power electronics, we have converters where we are using switches. So the switch could be either non-condition or off conditions. So if you look at any power electronic systems, one thing, they would be nonlinear in nature, like the other systems, other practical systems. But apart from that, they are not continuous systems, they are discrete systems. Meaning that when switch is on, you have one set of behavior, when switch is off, you have another set of behavior. So you don't have a continuous kind of a behavior, it's a discrete systems. So there is the exhibiting discreteness has introduced some challenges in modeling, but there are solutions to model such kind of a systems. In fact, the early work was done by Professor Middlebrook and Professor Chuk from California Institute of Technology in the mid 1970s, in 1976. So they proposed state space averaging and small signaling method for modeling the power electronic systems. What the state space averaging does is it just basically converts a discrete system to continuous systems. As I said, power electronics is basically a discrete systems. So to convert that into continuous, you need to use state space averaging. Now we use small signal modeling because the continuous systems obtained from state space averaging are not linear. So we need to linearize it. So just like other nonlinear systems, we linearize it by small signal modeling. So that is called small signal modeling. There are other methods also for linearizing power electronic systems, where we use averaged model for PWM switch. In fact, it was proposed by a researcher, Warperian, in 1990. Okay. So once we get a linearized model, we can use the conventional linear control theory, namely Nyquist stability criteria and Bode plot, to determine the approximate compensator. So the idea here is first to determine the model and then design the controller. Okay, I shall discuss about this in the coming slides. So before that, we'll see what is the state space averaging and small signal modeling. So I'll not be able to discuss in detail, but I'll just give you a flavor of what exactly this is. So we know that state equation, we are all familiar that state equation for a continuous linear systems is given by this expression. Now for a DC-DC converters, there could be multiple states based on switching conditions. Now those from power electronics background will be aware, but those who are not, please take this from a face value that power electronic converters would operate in two modes, mainly two modes. One is called continuous conduction mode, where the inductor current is always continuous. It's not zero, it's always above zero. And discontinuous conduction mode, where you have a period where the inductor current can become zero. So under continuous conduction mode, there are mainly two sets of state equations. One is when switch is on and other when switch is off. In case of discontinuous conduction mode, you can have three sets of state equations. One is when the switch is on, then the current through the inductor is rising, and when the switch is off, and there is still current through the inductor. And the other period is where the current through the inductor is almost zero. So this is for the conventional DC-DC converters, but some special DC-DC converters, even under CCM, you can have multiple switches states. For example, multi-port DC-DC converters or some high-gain DC-DC converters. In all such cases, we can have multiple states based on the switching conditions. You can also have multiple switches, so that can increase the number of states. So what the state, as I said, state space averaging approximates a switching converter as a continuous linear system. So in this next slide, I have an analogy. I'm not sure how relevant it is, but I just came up with this analogy to explain what exactly is state space averaging. So let us consider there is a light emitting source which emits light at a very high frequency. Okay, it emits light, say two different colors of light, one orange, another green. Orange during 0 to dt, where dt is some percentage of total time. Okay, and t is the frequency at which this light emitting source emits the light. And I'm assuming that the frequency of this operation is in the order of few kilohertz. Okay, so it emits orange for some time dt, and for the remaining duration, for 1 minus d into t, it emits green. Now, if I ask you a question that what is the color in that case perceived by the human eye? Well, one thing we can definitely say that if the period for which it emits orange is more, then the human eye would perceive it more, the color would be more orangish. Similarly, if the duration for green is more, the color obviously it's going to be more greenish. And if it's somewhere in between, then what could it be? It could just be some sort of an average combination of orange and green. Maybe you can just take orange amount of this, green amount of this, mix it and see what is the resultant color. Maybe that is the color that we perceive. So this is what we do in state space averaging. So I'll explain it how it is done in a DC-DC converter. It is done in basically 3 different steps. Okay. So what is the first step? As I said, power converters, based on the switch conditions, you have different circuit configurations. So the first step is identify those circuit configurations. So the first step is, for example, when the converter is on, you have one set of configuration. When converter is off, you have another set of configuration. It will become very clear when I show an example. Okay, when each configuration, the next step would be, step 2 would be, write the state space equation for each of these configurations. For example, when switch is on, you have one circuit. You can write the state space equation where A1 is the state matrix for that, B1 is for the output matrix for that, and C1 is the, B1 is the input matrix and C1 is the output matrix for this particular configuration. Similarly, for when the switch is off, you have another set of state equation. Now, just like the previous analogy, what we do is to get a continuous system, we just average the state equation to get one single average state space equation. So this is the average state space equation, which is a step 3. Okay, where here's the state matrix A is just the averaged value of A1 and A2. A1 into D, because this is on active for only D into T, and this is active for 1 minus D into T. Similarly for the matrix B and C. So this is how you get the average state space equation. So the aim for state space averaging is to convert this discrete system to a continuous system. That way we have achieved this. But if you look at the average state space equation, they are nonlinear in nature because they are defined by the set of nonlinear differential equation, mainly because the relationship between the duty ratio. When I say duty ratio, it is actually the time for which the switch is on, the percentage of the time for which the switch is on, and the other variables like output voltage and the other variables. So to linearize it, we construct a small signal model. It is just similar to how you obtain the small signal model for a diode. For example, this is the VI characteristics of a diode. To obtain a small signal modeling around the operating point, we inject a small AC signal. So the same thing that we do here, we need to inject a small AC signal. So we'll just see that in detail in the next slide. So here we can see that you have the state variable. You add an perturbation here in the state variable in the form of x cap. I think I missed out that cap. Okay, so where the small x is actually the small signal AC quantity. Similarly, the perturbations in V naught and duty ratio, the output voltage and duty ratio. Perturbation in input voltage is neglected mainly for simplifying the analysis. So if I introduce these perturbations in the average state equation, that is this average state equation, what happens is you get this resultant equation. This is what we get it. Okay. There will be other higher order AC terms which is neglected because the small signal, the square of a small signal quantity is almost zero, or multiplication of two small signal quantity is almost zero. So this you would get it. Now I can separate the DC terms. If I separate the DC terms, this is what I get. When I say DC terms, the which is represented by capital letters. Okay. And these DC terms, for example, if you take a buck converter, this basically gives V naught by V in, which is equal to D times, D times it will be equal to D. For boost converter, it will be 1 by 1 minus D, and so on. Okay. Now we'll see what happens when we separate the AC terms. If you separate the AC terms, you get this set of equation. Okay, so this is in time domain. Now to convert it into the frequency domain, I apply Laplace transformation. If I apply Laplace, this is what I get. And when I rearrange, this is what I get. This is the resultant. This is the resultant transfer functions. So there are two transfer functions. This is the control to output transfer functions and control to state output transfer function. Now, how do I identify the state variable in case of a DC-DC converter? State variables is nothing but an output of an integrator or something which is continuous and which does not change suddenly. For example, inductor current and capacitor voltage is considered as state variables. So you would basically, this will be a 2x1 matrix where the first row would be IL by D cap, that is inductor current by D cap, and the second row will be VC by D cap, which will be the capacitor voltage by the duty ratio. And this is the output voltage by the duty ratio. So these are the transfer functions which I use. So these transfer functions basically gives us the model for the DC-DC converter. Okay, I'll make it more clear very quickly with an example. So I've taken an example of a buck converter. Okay, so before I derive these models, I assume certain things. One assumption is I assume that switches and the diodes are ideal. And I also assume that the passive elements are linear, time invariant, and frequency independent. We can make these assumptions, even though practically they may not be true, but the model that is obtained still nevertheless is close to the actual system. Okay, so what are the steps involved in modeling? The first step is you need to identify the circuit configuration based on the switch condition. So when the switch is on, this is how the circuit looks like. Now, this is like a linear circuit. And then you apply the KVL, write the KVL and KCL and obtain the state expression, the state space equation during this condition. This is the first case. The next case is obviously we need to see when the switch is off. When the switch is off, you can again get another set of circuit where I formulate the state expressions. Okay, so that is the first step. Then the next step is, the second step is writing the state equation, and third step is getting this transfer function. So this is what I have done here. So I've just taken an example here where I've taken a buck converter with input voltage 8 volts, output voltage 5 volts, with other specification as shown in this slide. So with this, if I substitute the value of A1, A2, B1, B2, and the duty ratio, and so on, you would get this transfer function. Okay. So we are actually interested in these two transfer functions. One is the output voltage V0 by D cap, that is control to output voltage transfer function, and control to state transfer function. Here I'm only interested in IL cap. VC by D cap, I'm not interested because I anyway have V0 by D cap. That is more than enough. Okay. So this basically gives the model for the DC-DC converter. Okay, so I'll move ahead. We'll see what happens if it's a boost converter. If I do the same thing with the boost converter, I'll notice that this is what I get the transfer function. In IL by D cap, it's fine. It's similar to the buck converter. But if you see V0 by D cap, there is a particular thing, very important thing that needs to be observed. There is a right of plane 0 at 1.99 into 10 power 4 radians per second, or at 3.1677 kilohertz. Okay. And in fact, I saw a post on the WhatsApp group about right of plane 0 systems. So I'll just discuss that here. So in boost converter, actually there is a presence of right of plane 0, especially in the control to output voltage transfer function. So that results in non-minimum phase characteristics. What exactly that is, I'll not go into detail because there is lack of time. I'll just explain it in a very brief way, that because non-minimal phase systems add phase lag, meaning that if I give, say, a reference, for example, let us take a car. If I give a reference to turn right, for a moment it turns left and then moves right. In other words, if I give a reference positive, for a moment the actual output goes negative and then goes positive. The best example could be an aeroplane, where you want to, say, increase the height of an aeroplane, or you want to increase the elevation. So because you need to change the fins in such a way, for a moment the entire plane goes down and then goes up. Okay. So in such systems, there is actually difficulty in achieving high bandwidth control design, because if I try to increase the bandwidth, it would might result in unstable systems. Now, how is that exhibited? Why is that this behavior exhibited in boost converter? To explain that, let us see what is boost converter output to input voltage transfer function. Well, output to input voltage transfer function in boost converter is given by this expression: V naught is equal to Vs divided by 1 minus D, where D is the duty ratio. So suppose I need to increase the output voltage. What is that we need to do first? Obviously, the first thing that we need to do is increase the duty ratio. Okay, what happens if I increase the duty ratio? Okay, let us see the switch configuration. So this is the switch configuration of boost converter when the switch is on. So when the switch is on, you can see that the time for which the inductor is energized is more. Okay, the duration for which the switch is on is more, then that also gets more. And during switch on condition, please kindly note that the capacitor actually discharges, and that is what is ensuring that there is an output voltage. Capacitor discharges during when the switch is on. Now, to increase the output voltage, during off condition, it is the inductor, energy stored in the inductor is then transferred to the load. Okay, now if I have to increase the output voltage, the first thing, as I said, we need to increase the duty ratio. If I increase the duty ratio, the period for which I'm turning on the switch increases. In other words, the duration for which the capacitor discharges increases. So even though I want to increase the duty ratio, for a moment you would observe that the output voltage dips. So this is why we have that non-minimal phase characteristics, and mathematically given because of the right of plane zero. So that is momentarily, and after some time you would slowly, once the transients disappear, the output voltage would slowly build up when you increase the duty ratio. So this behavior is seen in some converters, not only boost converters, you can also see it in flyback and other converters. Buck boost converter also exhibits this. Whereas in other converters like buck and buck derived converters like forward, in that, or for push pull, in that converters, we don't get this right of plane zero because the circuit behavior is such that. In this case, the behavior is such that when I try to increase the output voltage, when I increase the duty ratio, for short time, the output voltage dips. Okay, so we'll see how do you design the compensator in such kind of a systems. Maybe I'll discuss it in the coming slides. Okay, so this is about, the first part was all about how do you model the plant. So we use state space averaging and small signal modeling, and we have got the model for the plant. Okay, the next step is we need to design the compensator. Okay, so I'm using the linear control theory for designing the compensator. And as you are all familiar that for the designing the compensator, the nature of the open loop transfer function, or the loop gain, is very important. You need to have a desired characteristics in the open loop transfer functions. Now, what are these desired characteristics? The loop gain transfer function is basically the compensator transfer function TC into TP. I'm assuming that the PWM gain is 1. Okay, so if you see the closed loop transfer functions, it is given by this expression. One thing that we know is that there should not be any steady state error. Okay, in other words, output by reference at steady state should be actually equal to 1. When I say at steady state, here we are all dealing with DC quantities. So at steady state means when the frequency is 0. That means when S is 0, you should get this transfer function to be equal to 1. Okay. And this is only 1 provided when T open loop is close to infinity. Okay, so one thing that we need to ensure is when we design the compensator, it should be such that the loop gain transfer functions, its gain at 0 frequency or at very low frequency should be very high as possible. Why? That is to minimize the steady state error. Okay, what are the other desired characteristics that is required? How do you design the compensator? What characteristics is required in the open loop transfer function? One thing is that the crossover frequency, that the frequency where which the open loop transfer function touches 0 dB or 1, that should be as high as possible, but an order below switching frequency. Now, why high? Why should it be high as possible? Well, it can be seen from the control systems that crossover frequency is also related to the bandwidth of the closed loop systems. And having a large bandwidth actually reduces settling time and increases speed. That can actually be mathematically represented by some set of complex equation, which I'll not be discussing here. But you can look into the control systems notebooks, textbooks, where you can see that if you have the bandwidth very high, then the settling time is reduced and the speed is actually increased. Okay. Now, but so we need to have a high crossover frequency, that is the open loop transfer functions where it touches 0 dB. That frequency should be as high as possible. But why should it be lower than switching frequency? It should be lower than switching frequency because it should not affect the system dynamics. It should not be so high that it affects even the switching frequency components. So it should be generally lower than the switching frequency. The thumb rule is the crossover frequency of the open loop transfer function is generally taken to be 1/5 to 1/10 times the switching frequency. That is provided there is no right half plane 0 in the system. We'll see what happens if you have right half plane 0. Okay, what should be the next desired characteristics? The next desired characteristics is the phase margin should be as high as possible. We all know that the phase margin and gain margin decides the stability. More the margin, the better it is. So that's why that is to take into account the other unknown disturbances and the imperfections in the modeling. For all that, we need to ensure that the phase margin is as high as possible, preferably greater than 45 degrees. And other things why we need to keep phase margin high is that phase margin increases damping ratio. That also can be mathematically represented. Phase margin actually increases the damping ratio if it is a second order system, which actually reduces the percentage overshoot. So having a good phase margin basically results in reduced percentage overshoot. So reduced percentage overshoot and less settling time is actually a good dynamic response system. Okay, so this is how the compensator should be designed. It should be designed such a way these three conditions are satisfied. What are the three conditions? One is that the gain at low frequency should be as high as possible. The other is the gain crossover frequency should be very high, but an order below switching frequency. And the third thing is that the phase margin should be in the range, preferably in the range 45 to 65 degrees. So you can use a PI controller, but I would use, which is being popularly used in power supplies, which is called a type 2 and type 3 compensators. I'll see, this is a systematic way how we can design this. It is actually similar to PI controller. So I'll explain how do we design a type 2 and type 3 compensator. First, I'll look into a type 2 compensator. So if you look carefully, a type 2 compensator, it's actually a product of an integrator and a lead filter. Okay, so lead filter, so that's why you know the zero frequency is less than the pole frequency. Okay. Now, you may be wondering why not only lead filter, why we need to have an additional integrator. Integrator is required because when you add a pole at origin in the compensator, what happens is you get this case. Okay, you would basically have where the open loop transfer functions gain at zero frequency becomes infinity because you have a pole at origin. So that's why you have the integrator. It is just, idea is to reduce the steady state error to 0. And lead filter to get a phase boost. Okay, at a desired crossover frequency. That's why we have this called type 2 compensator. So if you see the Bode plot of this is how it looks. Okay, so you have zero frequency, which is much close to the origin, the pole frequency, which is further away. Okay, and you have some sort of a boost somewhere in between. And if you try to realize it in an analog domain using op-amps, this is how it looks like. So if you see VC by V naught of S, then it would have a transfer function similar to this, where omega z, omega p, and a would be a functions of these parameters. Okay. Now, how do you design a type 2 compensator using a k-factor approach? Now, this is an approach, a systematic approach given by an industrialist. His name is Venable. There's a paper on it by Venable. He was working in a power supply industry, and he gave this approach. So I'll just explain this approach. The first step is select the crossover frequency to be 1/5 or 1/10 times the switching frequency. This is again provided there is no right half plane 0. So we'll assume that there is no right half plane 0 in the system. So the crossover frequency, I've taken it to be 1/5 to 1/10 times the switching frequency. Okay. Now for the lead filter, I've introduced a factor called K. When I know that the omega z is less, okay, and omega p is higher than omega z. So I take omega z to be omega crossover frequency divided by k, and omega pole to be equal to k times omega crossover frequency. So here the idea is to determine the value of a, omega z, and omega p. Okay. So now I have said this, but I do not know the value of k. How do I determine the value of k? That is the next step. Okay. So you know that the phase of the compensator at crossover frequency is given by this minus 90 because of the integrator, and this is the other expression. So this is the expression at crossover frequency. I'm assuming that there is a boost. So this quantity is represented by boost. So if I look carefully in this, and if I see this expression here, and if I substitute it here, I'll find that boost is tan inverse k minus tan inverse 1 by k. Or if I rearrange it, use some trigonometric formulas, I would get k to be equal to tan of 45 plus boost by 2. It's quite straightforward. You need not worry about it right now, but you can see it later. So this is how you can determine the value of k. Okay. Once I get the value of k, but to get the value of k, I need the value of boost, which I do not know what is the value of boost. That I'll get it from step 3. Okay. How do I get the value of boost? When I know the phase margin, which is actually, hello? I hope I'm audible and I can proceed, right?
Yes,
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 sir,
yes.
you're audible.
Okay.
Please, participants, see that the camera is off. I see few participants still with cameras on. Please kindly switch them off.
Yeah. Okay. Thank you, ma'am. Yeah. So now how do you determine the boost value? The boost is given by this expression here. We know that the phase margin is actually defined at the crossover frequency, which is actually 180 degree plus the phase of the entire loop gain, which is the phase of the compensator plus the phase of the plant. Okay. And I'm setting this to be called desired phase margin. Okay. And if I rearrange this, I know that the phase of the compensator is given by minus 90 plus boost. So if I substitute it and if I rearrange it, I get boost given by this formula. Okay. Now I should actually start with this step 3 and go step 2 and step 1. So what I would do is to get the boost, I would set the desired phase margin. And as discussed before, desired phase margin should be somewhere between 45 to 65. Say I'm giving 50 degrees. I give 50 degrees here. The plant's phase at crossover frequency would be known because I have derived the transfer function for the plant. So we have seen how it has been derived. So that was also known. So we can easily get the value of boost. Once we get the value of boost, we can get the value of k. Once I get the value of k, I can get the value of omega z and omega p. So if I look into this transfer function, I have got the value of omega z, omega p. Now what is the only unknown? The only unknown is the value of a. How do I get that? That's straightforward. You know that we have desired a particular crossover frequency. And when I say at crossover frequency of the loop gain, that is the open loop transfer function, its amplitude should be 1. That's correct, right? Because the amplitude should be 0 dB or 1. So by using this, I can get the value of A, which will be in terms of K and the plant's amplitude in terms of crossover frequency, at crossover frequency. So now we can see that I've got the value of A, omega Z and omega P with all the desired characteristics. So this is how we systematically design a type 2 compensator. Okay, but what is an issue with type 2 compensator? One issue is it has limited boost. It can give a boost of theoretically 90 degrees, but practically somewhere around 70 to 75 degrees. Under some cases, you may need more than that, a boost more than this value to achieve a good phase margin. So we go with something called type 3 compensator, where I have an integrator and 2 lead compensator multiplied, okay, with same 0 and pole. So this is bit complex than the previous case, but the advantage here is that you get more boost. We'll see that. It can be seen from the Bode plot. This is the Bode plot here, and it can be physically realized by this circuit here, by this analog circuit here. It can be seen that VO by VN in this case would be similar to this. Okay, for the type 3 compensator, the design procedure is almost the same. Only thing, the value of K, there is a slight difference. In the previous case, K is given by boost by 2, whereas in this case, it is given by boost by 4. Otherwise, the entire procedure remains the same. Okay. Now, if you look at the features of the type 3 compensator, it offers more boost for a given K factor. In fact, theoretically 180 degree, but practically close to 150 degrees, maximum possible. And you can see another behavior of this type 3 compensator is more low frequency gain which is desirable to achieve good steady state, zero steady state error, and less high frequency gain for a given crossover frequency compared to type 2 compensator. But the problem is it is complex compared to type 2 compensator, but nevertheless not that complex. But still, this is one of the drawbacks. Okay, so this is all about what I have discussed till now is how do you design the plant transfer function for a DC-DC converter? How do you design a compensator, say a type 2 and type 3 compensator for a given DC-DC converter? I'll just see some example. So a DC-DC converter works in 2 types of control. One is a voltage control. I'll say what exactly is voltage control. I'll discuss that. And the other thing is called current control of SMPS. There are basically two controls. Okay, what exactly is a voltage control of an SMPS? When when my intention is to regulate the output voltage of a DC-DC converter, then it is called voltage control. Okay, so the converter with this type of control is also called as grid forming converter. It's actually come from the inverters, but even here also we say it to be grid forming converters, mainly because it forms the DC grid. So there are two ways where we can achieve voltage control. There are two possible. There could be multiple ways, but this is one of the two ways which I would discuss, which is called single loop voltage control, where you would have only one compensator. Okay, and the voltage controller would directly change the output voltage by generating the duty ratio. Okay. Now, due to low time constant, when increase, the problem with this is due to the low time constant of the system, an increase in output voltage can result in high increase in current, and that increase in current can be drastic. Okay. So this high increase in current is not good from the hardware perspective, mainly because it can damage these switching devices. Okay. Another thing observed in single loop voltage control is that it has got overall poor dynamics. Okay. But the advantage here is you only have one set of controllers. It's easy. So for those where when your converter is over designed, you can actually use this. And where poor dynamics is all right, you can apply this method. We'll see how with some examples later on. Okay, there can also be a dual loop voltage control, and you have some sort of inner current control. Okay, so you have some inner current loop which which bandwidth should be much higher, and an outer loop with bandwidth should be much lower. Now, to design inner current control loop, you use this transfer function. To design this controller, voltage controller, you simplify this entire into one single transfer function, and then design this voltage controller. Okay, so here there is some current protection from the controller side, meaning that from the controller will not try to increase the current of the converter. Okay, but the issue is you need an additional current sensor. Current sensors are costly. When if you see any hall sensors, high bandwidth hall sensors can cost more than 1,000 rupees. So that is a drawback. But other advantage that we gain is that you can achieve much better dynamics. It is complex mainly because you need to design two sets of controllers. Otherwise, it's very popularly used for all the conventional DC-DC or other DC-DC converters. Okay, there's something called feed-forward voltage control. See, in the previous two control diagrams, you're actually waiting for the control output to change whenever there is change in, say, input. So if input changes, you'll have to wait for the output to change and then take the corrective action. What if we have a method where we can actually directly detect this input change? That is termed in control perspective called feed-forward. In fact, for such conventional or DC-DC converters, we can have a feed-forward control. This way, the delays are bypassed, and line correction can be virtually instantaneous. Even the starting transients is better in case of feed-forward control. When I say starting transient, when you start the converter at the beginning, so that time there could be high transients if you do not have this feed-forward control. That is where it's better to have this feed-forward control. But the issue is you need to sense the input voltage. So you have some price if you want to achieve something else. So this again increases the cost, but voltage sensors are not that costly. And if you have the space, then you can accommodate that. Okay, so this is some of the simulation results here, okay, which I have done it for boost converter, which I'll show you later on, where I've used this K-factor approach systematically. So I've taken a boost converter of this spec. In fact, this is a specifications which I was which I took it when we had to build a DC-DC converter for EV chargers. Okay, it was a SiC-based EV charger, so it is operating frequency at 100 kilohertz, meaning that the switches turns on and off 100,000 times in a second. Okay, so here the control specification is desired phase margin is 55 degrees. If you look carefully here, the desired crossover frequency is not 1/10 of the switching frequency. In fact, it is taken as 1/10 of RHP0. See, this is one way of encountering this RHP issue. One way is you can reduce the bandwidth such a way that the effect of RHP doesn't come into picture at all. But what is the issue? The issue is you're trying to slow down the system a lot. And in applications where this is all right, this slow response is fine, we go ahead with this approach. There are other approaches where they use mainly nonlinear control to overcome this RHP0. But if you're using linear method and if you're using this K-factor approach, one possibility is you can have the crossover frequency not to be equal to 1/5 or 1/10 of switching frequency, but below this RHP0. In this case, I think RHP0 was somewhere close to 3 kilohertz. So I have kept the desired crossover frequency to be 300 hertz. Please note here we are operating at 100 kilohertz switching frequency. Okay, and here I have designed a type 3 compensator mainly because at this desired crossover frequency, the phase boost requirement was somewhere close to 130 degrees, which could not be achieved with type 2 compensator. That is where I have designed type 3 compensator. So this is the Bode diagram of the loop gain transfer function, where we can see that the desired phase margin is achieved at that desired crossover frequency. Okay. And this is the simulation results where I have changed the reference from 400 to 350 volts. There is a bit undershoot, mainly because the crossover frequency is very small, so the dynamic performance may not be that good. But in applications where this is all right to take care of this issue, we can go ahead with this approach. This is what this is the simulation results or voltage control. It's a single loop voltage control for a boost converter. Now we'll see current control. What is exactly current control? Here the current control is to regulate the inductor current. So in voltage control, we need to use V naught by D cap as the plant model. In current control, we need to use IL by D cap as the plant model. Okay, that is basically comes from the state to our control to state transfer functions. Okay, so the aim is to regulate the inductor current, which basically indirectly regulates the output current of the converter. So in some applications, we need to regulate the current rather than the output voltage. We'll see that which are the cases. So converters which operating in such scenarios is called grid feeding converter, because it feeds power to the grid. Okay, so in such converter, the output voltage is regulated by some other source. Please note that current controlled converters do not operate in standalone conditions. It's rarely used in standalone conditions. You basically use current control converter in collaboration with some other converter. You have some other converter also, or some other source which tries to regulate the output voltage. Okay, so there are three different types of current control. One is tolerant band or hysteresis current control. There is something called peak current control, where you're trying to control the peak of the inductor current. There could be, it again has some different subtypes like constant turn-off time control, constant frequency control. But I'll just try to focus on average current control, where I'm trying to control the average value of the inductor current. Okay. So this is the control loop. Again, you would have seen this control loop in the dual loop voltage control. So again, here to design this compensator, this would act as the plant. That is IL by D cap and a low pass filter. And then again, you can have a type 2 or a type 3 compensator. Mostly here, type 2 compensator would suffice, because current controller, in fact, it can be approximated into a first order transfer function. Even a normal PI control can be used. Current control is actually relatively easy than the voltage control. Okay. So this is the simulation results for the current control for a boost converter, where if you notice here, the control specification is desired phase margin of 55 degrees and desired crossover frequency of 1/10 the switching frequency. So I've kept it as 10 kilohertz because it's a 100 kilohertz system. And type 2 compensator was more than enough because the required phase boost was less than 50 degrees. Okay, so this is the loop gain transfer function here as shown here. You can see that the desired phase margin is achieved at the desired crossover frequency. And this is the inductor current. The red one shows the reference value. So the black one is the actual inductor current. There will be a ripple because inductor current would always have a ripple. That ripple can be reduced by having a much larger inductance. But anyway, this is how it is, and it can be seen that there is very good dynamic response in current control. Okay, so this is all I have explained is right now the analog, how do you design it in the control and the analog domain. I'll just give a brief light into how do you implement it in digital. See, in most of the today's application, power electronic systems, they come with a digital controller. Mainly because the digital controller needs to do some other operations. And nowadays, most of the systems are smarts. Even in electric vehicle, you don't have any analog implementations. In most of these systems, it is mainly digital. Okay. So in the recent years, digital controller design for power converter has been an active area of research. Now to implement in digital form, there are two main approaches. One approach is you can design the controller in analog domain, that is using the continuous time S domain method, and convert the controller transfer function from S domain to Z domain. It's very popular. This technique is popular mainly because it relies on the traditional design techniques. But what is the issue? See, the issue is when you try to convert it from S domain to Z domain, you would have designed the compensator with some target in mind. That is some specific settling time or minimum overshoot with some phase margin and so on. But when I convert it into Z domain, there are various ways to convert it. When you convert it, you lose that behavior. Okay, so there is a mismatch between the original analog and resultant digital. But one thing is we can minimize this mismatch, maybe using some better transformation, which is called Tustin transformation. In power electronic systems, I have seen from my personal experience that generally Tustin transformation or bilinear transformation or trapezoidal rule, that different engineers call it with different names. A mathematician always would say trapezoidal rule, but a control system maybe person would say bilinear transformation. So this is the use. If you use this transformation, this mismatch is minimized, at least in power electronic systems. I'm not aware of the other systems. So this is one approach. What is the other approach? Other approach is directly in digital design. That is, controller can be designed directly in Z domain. For that, you need to use the discrete control concepts, where you use discrete time model, approximate discrete time model for the plant, and then design the controller. But it's not popular. Even in industry, I have seen personally, at least in Indian industries, this method is not popular, mainly because it's more mathematically involved and there is a lack of knowledge. When I'm not familiar with this technique, and it also lacks a strong link to the traditional analog controller design methods. So I'll just see how do we. I've actually done this approach where I've done the compensator design in S domain and then converted it to the Z domain using bilinear transformation. So this is the bilinear transformation where T is basically the sampling time. Please note the sampling time is different from switching time. Sampling time is the time at which your ADCs in the digital controller samples the waveforms. One thing to be noted is that this sampling time should be as small as possible. Smaller, the more smaller, the much better it is. Okay, at least less than or equal to the switching frequency, switching time period of the converter. Okay, if you keep very small, the issue is you would have very little time to compute the entire control algorithms. If your controller is very fast, then you can keep T to be very small. But yeah, anyway, this is the rule here. In other words, the switching frequency should be, the sampling frequency should be greater than the switching frequency. Okay, so I have actually done a MATLAB simulation, which I will show you to you later, where I have, what I've done is, I have followed the analog approach and designed the same compensator. Now I have applied the bilinear transformation. Say I have applied to two terms, one is the integral term and another the lead term. If I apply the bilinear transformation, there is actually a code in the MATLAB which does that. I'll even show you that. So there is, you will get this expression. I think the code is C to D. Okay. So this in an analog form is this way. That is y. If I multiply, cross multiply here, this is y present is equal to y old. That is y n minus 1 plus some term into x present, where x is the input to the integral term, and some term multiplied by the x old. So this can be directly converted into pseudocode in your embedded controller. So when you want to implement something, you can directly write it. Okay. So similarly for the lead term, you just apply the bilinear transformation here, you get this. So I'll just show the simulation later on once I complete my slides. How do you implement the digital control of a current controller? Okay, so this is how I have, in fact, in MATLAB, even in the simulation, in Simulink model, you can actually convert the S domain transfer function into Z domain through this block diagram here. Okay. So this is the simulation results again in discrete domain. There is slight lag in the digital domain than in continuous domain, but that's also fine here. It can be seen that the actual inductor current tracks the reference, average reference current. So let's see where these voltage and current control are employed in actual real-time systems. This is very important, a very good knowledge of where it has been applied. So one such application is where we use DC microgrids. So DC microgrids, there is some microgrids are the future technology, and DC microgrids is one of the candidates for the future technology. When I say DC microgrids, you have various set of DC-DC converters with various sources and loads interconnected to form a DC grid. Okay, now one approach is we need to identify which are the converters I need to operate in voltage control and which are the converters I need to operate in current control. So I have some converters which is connected to renewable energy source like PV and wind, and some converters are connected to battery, and one other converter is connected to AC grid. See, the converter which regulates the output voltage, its power would depend upon the external condition. It depends upon what would be the load in this entire network, because only its job is only to regulate the output voltage, not to regulate the current. So based on the loading conditions, it should be able to supply that amount of current. So generally a source which is dispatchable and which is completely controllable, only those converters are operated in voltage control. And if I see here, I will definitely not operate PV and wind connected converters in voltage control, mainly because they are not deterministic. They depend on the external environmental conditions and so on. So here the best candidate would be AC grid, because the AC grid can supply any amount of power and it's only limited by the converter design. So you can actually pre-design and say that, okay, this is the power handling capability in the network. So I will design this converter in such a way that I regulate here in voltage control mode. And I can keep the remaining all in current control mode. That is fine, but issue is our AC grid is also not reliable. Sometimes this can fail. If this fails, somebody else should take over. So one approach is even battery is considered as a completely dispatchable source. So generally 4 and 5, these two converters are operated in voltage control and the remaining converters are operated in current control. For example, in PV, the current reference would come from the MPPT algorithm. Similarly, for wind, the current reference would come from the MPPT algorithm. And that is how you operate this entire system as a team. One thing to be noted is when you have 2 or more converter trying to regulate the output voltage, slight mismatch in the output voltage can cause large circulating currents. That is traditionally resolved using something called droop control, where you add drooping characteristics. I'll not go into detail for this, but where you add drooping characteristics into the control loop. This is similar to connecting 2 synchronous machines in parallel. Okay, which is trying to regulate the output voltage and frequency. The same thing in DC-DC converters. When you have 2 DC-DC converters controlling the voltage, then you need to have some sort of a droop control or some sort of a communication. So this is something more advanced, but to understand such advanced control, you need to understand the basic voltage and current control for the various DC-DC converters. The next important application is a PFC converter, which is employed very frequently, especially for battery charging applications. For even electric vehicles, you have PFC converters being used. You have various LED drives. Most of the LED bulbs also comes with PFC converter. So this shows the circuit layout of the PFC converter. Here, those who are not from power electronics background, you need not get worried. I'll just give you a basic idea. So here, what it does is, the basic idea is to ensure that the current from the grid is unity power factor. That is the requirement for the power systems, because if you have, maybe if you have only one element, it is fine. You can use a traditional H-bridge rectifier. The diode bridge rectifier, but if you have many of such converters, it's always good to have unity power factor from the grid. Okay. That is to ensure there is no harmonics from the grid. Okay. It is from the requirement from the power systems. And there we use actually a boost converter. And in fact, whatever I have discussed earlier, that is voltage and current control, that is being used in such converter. So if there is someone who wants to implement a PFC converter, he or she should know how to implement a current voltage control for a conventional boost converter. So here the idea is same, the outer voltage control with the inner current control, but only thing here is the current is not a fixed reference. The reference is some sort of a rectified sine wave. So that rectified sine wave is such that it should be synchronized with the grid so that you get a unity power factor. Okay. So what I want to convey here is, to design such systems, we need to know a basic control for say a boost converter or a DC-DC converter. So this is the simulation for a PFC converter. So here, these are the control specifications. So if you see here, the crossover frequency, I've kept it very small. For the outer, for the voltage controller, it's around 5 Hertz. Okay. Mainly because for the voltage, you have, since it's a single phase systems, you would have 100 Hertz components if this is a 50 Hertz component. So that is why I have deliberately slowed it down. Anyway, I'll not go into that in detail. Okay, so you can see that the output voltage of the PFC converter is regulated to the reference 450. Here I changed the reference to 430 and it is there. The poor dynamic response is mainly because the crossover frequency is much smaller. Okay, and this is the grid voltage and grid current here in this diagram, where it can be seen that they are always in unity power factor. So again, the knowledge required is, again, what is the design control of DC-DC converters. So I'll move ahead with the last section, which is the control of inverters or DC-AC converters. Before I move ahead, any questions which you have? Or Elizabeth ma'am, shall I continue with the presentations? And maybe the question would be taken later.
Yeah, there are quite a lot of questions. So I think towards the end, we shall
Okay.
look into it.
Okay, madam, fine. I'll look into it at the end. Fine, so I'll move ahead. I'll discuss the last section for this presentation. So that is the control of voltage source inverters. Again, it's a very vast topic. I'll not be able to cover everything, but I'll just give you a flavor of what exactly is control of DC-AC converters. So this, what exactly is voltage source and converters? It converts DC to AC or the other way around. They're extensively used in various systems. One thing I can tell you, they're used in UPS systems, the inverters, the motor drives, standalone and grid-tied renewable energy source systems. In power systems, they're used in STATCOMs, in the transmission side, active filters in the distribution side. high voltage DC is nowadays today. Previously it was, you are definitely have inverters there. Load emulators. In fact, if you would have seen some of the laboratory equipments, you have something called load emulator, which emulates a resistive load, a capacitive load, an inductive load. All that is possible by having a voltage source inverters. Now, there are different ways you can classify voltage source inverters, but I have classified based on the operation and based on the device technology used. So one is the early inverters were thyristerized inverters, where we're using SCRs in the early inverters. The inverters invented in 80s and used extensively in 90s, especially today in HVDC, they are used thyristerized inverters. The other set is the resonant inverters, which is used in, say, induction heating. All our induction cooker is actually, you would have a, not cooker, induction stove would have resonant inverters. Then there is something called MOSFET or IGBT based inverters, which is extensively used in other applications. In fact, all the modern inverters, all the thyristerized inverters are now being replaced by MOSFET or IGBT or SiC based inverters. They are again classified based on the gating pulses. You can have square wave inverters. If you see the early UPS, UPS in the late 90s and early 2000s, they were all square wave inverters. Today we have all PWM inverters. The UPS systems also have PWM inverters, where you have sine pulse modulated or space vector modulated, so on. And the inverters are also classified based on the number of levels. You have something called 2-level, multi-level. Okay, there are some multi-level itself. You have modular multi-level and so on. There are some special inverters like Z-source inverters. Some inverters which integrate the DC-DC also into it. So there are various researchers have given various types of special inverters. But if you look at the conventional full bridge MOSFET or IGBT based inverter, this is how it looks like. You have a DC port, you have a full bridge, you have an AC port. In AC port, again, you have the filter part and the grid part. Like DC-DC converters, here also there are two types of control, voltage control and current control. One is called grid forming, that is voltage control, and grid feeding, which is the current control. Okay, now let us see the current control. So again, to design the current control, you need to model the system. Fortunately, modeling of inverters is quite straightforward. It's not that you need not use state space averaging. We use the averaged model. If you use, if those who are in power electronics domain would know that if you have a sine pulse with modulated full bridge inverter, the fundamental value of the terminal voltage is given by MA into VDC into sine omega t. That's known. You would also have the harmonic components, but that will be in the switching, in the order of switching frequency, and it doesn't matter for this filter. Okay. So if you apply KVL and KCL, you will find that IG is actually, the grid current is actually VT minus VG divided by this impedance, which is given by this. And graphically, in a block diagram form, this is how it is. This is the model, average model for a full bridge voltage source inverter. So just by having this model, we can design the compensator. Okay, I'll see how do you design the compensator. Okay, this is the control diagram here. Okay, so you have a full bridge. This is the model which I showed in the previous slide, this entire model here. Okay, you need to, I'm doing the current controls. I'm trying to regulate the output current, which is the grid current. I'm giving some sort of reference. Now, please note here, I also have PLL. Now, PLL is again a control system. Okay, I'm not going to discuss that again. Even PLL is basically to track the reference, the fundamental reference of the grid voltage. Even in PLL, you have a compensator. So there is a lot of control systems in power electronic systems. Okay, anyway, right now you assume that this PLL is just, which generates a unit sine wave, which is in phase with the grid's fundamental component. Okay, so I got the reference current, I have the actual reference current, you have the controller, which is then divided by VDC to get the modulating index, which is M sine omega t, and that is limited by a limiter, and then you have the modulating index, which is realized using some sort of PWM method. Okay. You can also have some sort of feed forward here. So for example, here I have taken the grid voltage and fed it back. So this is a much better control. As I said, feed forward always eliminates it can bypass all the lags that comes into the system. So you can also have a feed forward, and you need to have some sort of a feed forward filter. Even directly feed forward is also possible, not an issue. Okay. Now I'll discuss how do you design now the next question to be asked is, we have seen how to model a voltage source inverter. Now the next question to be asked is, how do you design this controller? Now, what are the candidates for the controller? Let us see, there are two candidates which I would discuss here. One is a PI controller. Okay. The PI controller is Kp plus Ki by S, and this is the plant transfer function, which is 1 divided by SL plus RL. This is provided you just have an L filter. You can have multiple, nowadays you have LCL filter, and LCL, LL filters, and so on. But I've just taken a simple systems. For other systems also, it is the methodology is same. Okay, so this is this thing. Now here you can see that the loop gain transfer function has a pole which is minus RL by L. Small RL is actually the ESR of the inductor, which is quite small. And this quantity, this pole is very close to origin. The problem with it being close to the origin is, even though the system is stable, it leads to slow natural response. So what is the solution? One solution is you can cancel this pole through a compensator in the what you call in the compensator. Okay. So if you rearrange this term, in fact, you can see this way. So to get a good response, you can actually keep Ki by Kp to be equal to this. So you are actually cancelling the pole of the plant through 0 of the compensator. Okay. If you do that, I would basically get the loop gain transfer function in this form, okay, where tau I is the time constant. And if I try to obtain the closed loop transfer function, which is loop gain divided by 1 plus loop gain transfer function, it is given in this form, which is just a first order systems. So based on the value of tau I, you can get a very good closed loop, good response. If you keep a very low value of Ti, you will reach a very good steady state error, and there is not going to be any overshoot here because it's a first order system. Okay, but now let us see. See, we are not dealing with DC quantities here; we are dealing with AC quantities. So if you look closely at this closed loop transfer function, you can see that it is actually similar to a low pass RC filter. Okay, and this closed loop transfer function is nothing but Ig1 divided by Ig1 reference, okay, where Ig1 is the input and Ig1 reference is the output. If it is DC, I understand that at steady state this is always going to be the input voltage. But if it is AC, what inference can we make? One thing is sure, because it's an AC systems, there is going to be, the amplitude is going to be very small, and there's going to be phase shift. So PI controller is actually not suitable for sinusoidal current reference tracking, because this magnitude of this closed loop transfer function at the grid frequency omega naught is not equal to 1. It is actually less than 1, and the phase is not equal to 0. Okay, so PI controllers cannot be used, but we can minimize the error by ensuring this value of R is very small. When R is small means this time constant is small. That is, this R is very negligible. Yeah, that way you can do that. Okay, but anyway, this is not desirable because there's always going to be some sort of steady state error. So what is the other solution? The other solutions is, there are actually multiple solutions. What traditionally people use is, they try to convert this AC quantity to DC quantity using some sort of matrix transformations. Okay, like they use something called Clark's or Park's transformation, get it in DC, and then use PI controller and then retransform it. That approach is that what people generally use. But I'm going ahead with some other approach, which is called resonant controllers, where you can directly deal with DC quantities. See, one of the reasons why the PI controller, the problem is that you don't have any steady state, you have a steady state error. To eliminate the steady state error, we know one thing, that the loop gain transfer, the closed loop transfer function at grid frequency should be 1 angle 0. Okay. That is only possible when the magnitude of the loop gain transfer function at grid frequency is infinity. So what we do is, we need to add a complex conjugate pole in the compensator at grid frequency. So the first step is have the compensator in this fashion. This way, I can ensure that the steady state error is going to be 0. What are the other conditions? Now our job is to find out this H of S. Now to find out the H of S, we need to ensure two things. One thing, the phase margin should be greater than 45 degrees. That is for the obvious reason that the phase margin should be as high as possible for a much better stability. And the closed loop bandwidth should be as high as possible. Again, closed loop bandwidth is related to the loop gain crossover frequency, and it is given by this relationship. And the closed loop bandwidth is somewhere kept to be 1/5 to 1/10 the switching frequency. So you can find out what is the loop gain crossover frequency. So by that, so H of S should be such a way that these two conditions need to be satisfied. Okay, let us see what will be the Bode plot when I keep H of S equal to 1. That is just 1 divided by S square plus omega G square, where omega G is the grid frequency, which is 50 Hertz. So this is the Bode plot. This is how it looks like. And my desired closed loop bandwidth should be, or this, it should be very close to 12,500 radians per second. Now, if you see the loop gains crossover frequency in the order of this, you can see that the phase is minus 270 degrees. So in other words, phase margin is negative. So it's an unstable system. So what do we do next? We can see that this excessive low loop gain phase is mainly because of the pole of the plant, which is, what is the pole of the plant? Plant's pole is at, this is the plant transfer function. The plant's pole, so the plant's pole is at minus R by L. It is at minus 8.69 radians per second. Therefore, to improve the loop gain phase, what you can do is, in compensator, I introduce a 0 to cancel the pole of the plant. So this is what it is. So this is the Bode plot, which shows with pole cancellation and without pole cancellation. The one with orange is with pole cancellation. You can see that the phase has been improved. You can see now the phase at the order of 12,500 or 12,000 radians per second. It's around minus 180 degrees. Okay, the phase has improved, but still phase margin is 0, still not sufficient. Okay, so one way we have introduced a 0, which is equal to a pole at the compensator, which is equal to the pole at the plant. So that way the phase has been improved, but not sufficient phase boost. So the another solution. So what is the solution to it? The solution is you add a lead filter. Okay, you all know that the lead filter is given by this expression, where the 0 frequency is much less than the pole frequency, and the angle at which you get maximum boost is given by this expression, and the frequency at which you get that boost is given by this expression. Okay, so what I can do is I can design the value of P1 and alpha such a way that delta M. Yeah, so here the unknowns can be found out by such a way that delta M is kept greater than 45 degree and omega M is kept to be equal to omega C. And this value of H can be determined by knowing that the loop gains transfer function at crossover frequency should be 1. So that way we can get the value of H. So in this is the final compensator where you get the value of H, we get the value of P1, we get the value of alpha 1. Everything is known. Okay. So to improve it more, we can also add a lag filter. This is just done to enter have a large magnitude. It's not compulsory, but if you have the lag filter, it's much better. Okay. So you may also think that why not you add a integrator. You can also add an integrator, but problem with an integrator is it introduces a minus 90 degree lag at all the frequencies. So to avoid that, we can add a lag filter, which is a much better option. Okay. So if you do add a lag filter, it doesn't affect the quantities at the high frequencies. Only at the low frequencies, it improves the what do you call the magnitude, and it creates a small phase dip, but that's all right. And so this is the final compensator, and here you can see the Bode plot of the loop gain with and without lag filter. So you can see at the high frequency terms, it doesn't matter. It's just that the low frequency terms with lag, you have a very good, the gain is much higher. So it improves, that is how you design a resonant compensator. Okay. It is a bit complex. You can see that there are a huge number of terms. You cannot be physically realized. I'm not sure if it can be realized in analog domain, but definitely it can be realized in digital domain. You can convert this to digital and implement it. It would definitely work. It's a systematic approach and it would definitely work. Okay. But yes, it would be computationally intensive as you have so many terms in the compensator. So that is about the resonant compensator. To simplify this, there is something called proportional resonant controllers, which is there, which is nothing but a special case of the resonant controller. Okay. So those who are interested can see some of the materials related to PR controllers, which is extensively used in control of voltage source inverters. Okay, so this shows the simulation result and the current control, where I'm trying to control the grid current. So I'll show you the simulation also, where you have the grid currents, which is shown in orange, and the grid voltage, which is shown in black. And here you can see that I have changed the current reference from 400 ampere peak to 250 ampere, and you can see that instantly there is a change in the current reference. Okay, here I've done the change in reference from minus 250 to minus 250 ampere. Initially, I kept it 250 ampere. So during this mode, the power is going from the DC to AC port, and from this time, it is going from the AC to DC port. Okay, so I need not do anything in the control on the converter side. Only thing I just need to change the current reference from 250 to minus 250. And voltage source inverters are inherent bidirectional, so these effects would be taken care of. Okay, so that is about the current control of full bridge voltage source inverter. I'll very briefly explain, I think it's almost time, I'll very briefly explain the voltage control of full bridge voltage source inverters. So in the previous case, I was trying to regulate the output current, and the output voltage was regulated by the grid. Okay, you had grid here. But in this case, I'm trying to regulate the output voltage. In other words, I am forming the inverter is forming the grid. Okay, if you try to think of an application, best example could be UPS application, where when the grid fails, it is the job of the inverter to regulate the output voltage. Okay. So here is where we use voltage control. So the method employed is again same, average output voltage control. You can use PI controller as well as we can use some sort of a resonant controller. I'll show you, I have worked in UPS in projects when I was in L&T, and I know how the control loop is designed. So if you look into most of the Indian industries, I'm not sure about the foreign OEMs, but in Indian OEMs, you can definitely find that you would have such kind of control loop. Okay. What we do is we rectify this output voltage, the desired output voltage, and try to compute the average value of the rectified signal. Okay. The reference is kept as 230. This is the RMS value. So that is converted to some sort of an average value. There's a formula to it. And then use a simple PI and then regulate it. So this works well. It's very simple. Even the PI controller design here is very simple. Okay. Only thing here is the PI controller should be designed such a way that the overall loop gain cutoff frequency should be very small. Mainly because this average computation takes at least one switching period. Okay, at least one half cycle. So that's the only thing to be taken care while designing the PI controller. So with this, you can actually control. But the issue is if you want to add more smart features, if you want to increase the speed, this will not do good. Mainly because you will have to wait one half cycle to have some correction in the entire control loop. Okay. So the another, I'm sorry about the typing error here. So this is an instantaneous output voltage control. Okay. In fact, very few people I could see that when I was working in industry, very few people knew about the resonant controllers. I'm not sure what are the foreign OEMs, like some of the companies like American Power Company, which makes UPS, what control technology they use, I'm not sure. But this could be a very good candidate for voltage control, because here the response is much better. You're trying to control the instantaneous output voltage and have a resonant controller. Only thing is you need to model the system appropriately and design this resonant controller in an appropriate systematical fashion. I'm not showing the simulation results for this, as it is similar to the previous case. So the conclusion and reference. So the conclusion is the control strategy, selection and design is critical for the power electronic systems. In fact, it is seen that the control algorithm is the brain for the power electronic systems. There are two main approaches for modeling the power electronic systems. One approach is small signal averaging, state space averaging and small signal modeling. The other approach is the averaged switch model or average behavior of the converter. K-factor approach is extensively used for the control of switch mode power supply. And for a voltage source inverters, better dynamic performance is achieved with resonant controllers. So these are the references. I haven't referred much papers. In fact, the conventional textbooks by Professor Ogata, you can also refer other control textbooks like Norman Nice for the control system part. For the power electronics part, I've used Professor Ned Mohan's textbook. It is well explained, the control part. I think chapter 10 in the latest edition explains the control of DC-DC converter. Now, this is the paper which I was talking about. It is by the industrialist Dean Venable. In fact, he gave a systematic way of designing compensators for DC-DC converter. This paper is available online. It is an open source. You can just type it in Google. You can get this paper. Then for voltage source inverters, I would recommend a textbook by two Iranian professors, and the Professor Irvani, who is actually working in a university in US. It's a very, very well-written textbook. I found it to be quite useful. So those who are interested in the control of voltage source converters can refer to this textbook. It is a bit costly. It's around 10,000 rupees, but it's worth. I would definitely say that. So before I close, I would say that since most of you are faculties, I think when I was a BTech student or when I was an MTech student, I didn't realize the importance of control systems in power electronics. But as a faculties, I think we need to strive to ensure that we teach the students the importance of control. In fact, some of the faculties can even introduce this course in your college as a control of power electronic systems. The other advantage of this subject is that you can actually show it in actual practical systems. You can also have a laboratory component with the control of power electronic systems. And nowadays, the digital control is becoming quite popular, especially among the students. So you can also explain it how systematically we can do it. Because what I see is, even in industry, people use design PI controller by just hit and trial methods, which may not be a systematic way and might consume a lot of time. So this, what I have explained, is a systematic approach. So that's it from my side. Whatever I have with my experience, I've explained. I hope you found this useful. I understand this could be a very quick, and it is too difficult to listen to me for, I think, 1.5 hours. But my intention was to give the flavor of the control of power electronic systems. And I hope I have done that. Yes, Madam Elizabeth, ma'am, over to you. If there are any questions, I would be happy to take it.
Yes, Dr. Prajof, definitely you have given a briefing or I think a wide spectrum of topics, and it's interesting, and as faculties we can catch up on those.
Yeah.
I shall start with the questions, I guess.
Yes, madam, you can start with the questions anywhere.
So the first question is, which type has more advantage, isolated or non-isolated?
Okay. Yeah, actually, which type, it depends on the situation. If you ask me with this question, what I would say is non-isolated converters. See, if you don't need an electric isolation between the output and input, and if the gain is not that high, I would generally recommend non-isolated converters. Okay. Isolated converter, the issue is that they have a transformer, so the efficiency will be low. But the advantage with isolated converters is that you can achieve very high gain because of the transformers. And some of the isolated converters are used in very high power level. In fact, if you see in industry, dual active bridge is extensively used for EV charging applications. And even the other applications, isolated converters are used. So my answer to this question would be isolated when you need electrical isolation and when you need high gain, and non-isolated when you don't need electrical isolation and when the gain between the output and input is quite small. And when you want to reduce the complexity, I would definitely recommend non-isolated converters.
Okay, and next question is, can you brief on multi-port DC-DC converters?
Okay. So whatever I have shown here, they're all two-port DC-DC converter, meaning that you have one input port and one output port. Now, the problem with two-port DC-DC converter is if you need to say integrate PV and wind to the to the grid, I need to use separate DC-DC converter for PV, separate DC-DC converter for wind, and integrate it. The drawback with this approach is I need to have two set of converters and two set of control algorithms. Now, what if I can come up with a method wherein I can connect both PV and wind to a single converter? Okay, so that means I have two input ports and one output port. Okay, or what if I can come up with a method where I have multiple input port and multiple output port? There are some applications which demands that. Those converters which does this job is called multi-port DC-DC converter.
Next question. When we are doing state space model, what are the criteria to choose the state variables?
Okay, here in power electronic systems is quite straightforward. In fact, state variables comes from, as you know, it is the integrating output. Okay, so if you see in any power electronic converters, you basically have inductors, capacitors, resistors, switches. I don't think there is anything else in power electronic systems. So the inductor is actually inductor current is actually the integration of inductor voltage, and capacitor voltage is nothing but integration of inductor current. So it is the inductor current and capacitor voltage which is the state variables, mainly because they are continuous, they cannot change instantaneously. Inductor current cannot change instantaneously. Similarly, capacitor voltage cannot change instantaneously. So it is always these which is taken for power electronic systems. I'm not aware of the other systems. I hope I have answered it from a power electronic engineer perspective.
Okay. Next is how to calculate phase margin and gain margin without using the conventional plots like Bode or polar plot.
Well, I myself do not know that. Madam, I do not know. You are from control domain. I am not sure if there are any other methods.
Okay. Next question is, which control is practically used? Is it the voltage or the current controller? And is there any criteria for selecting it?
Yeah, that is what I explained.
Yeah, India voltage control.
So what I want to say is that voltage control is used when you want to regulate the output voltage and when the source is able to supply that much power. Because when you use in voltage control, you don't have any control over the output power. It depends on the external conditions. Your job is just, the converter job is just to regulate the output voltage. Okay, so based on sometimes the load conditions can be such that the load can be negative. In other words, the power flow can be from the load side to the source side. So the converter also should be bidirectional if you want to ensure the low voltage control. Generally, for renewable energy sources, it is the current control. Very rarely we use renewable energy sources in voltage control. We never use that. It's always in current control, and generally these stiff sources like battery. Even battery sometimes is used in current control. In fact, while charging the batteries, if you charge the lithium-ion batteries, they are charged in constant current and constant voltage. When I say charging the battery in constant current, it is in current control. When I change in constant voltage, it's in voltage control. Okay, so this depends on the applications. Yes.
Yeah. Next question is, for solar PV application, DC power control, which converter is good, buck, boost, or chuck converter?
That again depends on various cases. Buck boost is good because it can track the entire PV characteristics, but it need not be, because sometimes we may have to use some other converters. It again depends on the applications. So how do you get that? That all comes from a good knowledge of these converters. So from that, automatically you would know that when to use which converter. And based on the applications, we have to select that appropriately. But otherwise, if you compare these three, buck boost is more reliable, most better for PV application, mainly because it can track the entire PV characteristics.
Okay. Next is which type of converter is used in a domestic LED bulb and LED batten, and which type in newer types of inverter bulb with inbuilt battery?
Okay, the first part was which was the converter used in LED
Used in
systems, isn't?
LED bulbs.
Okay, again, no OEMs will disclose which is the converter they use it. What I can say from my experience is that we would have a range of converters which can be used like the conventional buck and boost or some sort of isolated converters. But otherwise, in the commercial LED systems, it's a trade secret by the individual companies. So then nobody would disclose that. Otherwise, as a researcher, we can try out different methods. We can have all the converters. If you see the research papers by well-known researchers like Professor Beam Singh's students, I have seen he works extensively on LED-based systems. He has come up with, I see students coming up with various topologies like Sepik, Chuk, and they have some sort of zeta and combination of these converters, DC-DC converters. Ultimate idea is to show somebody that this converter, by using this converter, we have achieved this much improvement in efficiency or this much reduction in cost.
Okay. The next question is, sir, can you explain about adaptive control in boost converters? And
Okay.
how about the switching frequency control like ZVS?
Okay, I'm not worked on adaptive controllers. I've not seen people using adaptive controllers for boost converters. So I'm not aware of these, to be frank. But what I've seen is people nowadays are using for boost converters because of its RHP 0. I've seen one of my lab mate used IMP, I think internal mode. I'm just not getting that IMC control, the full form of that. And some are using sliding mode control, but in industry, I've never seen, at least in Indian industries, I've never seen such nonlinear control being used. About the adaptive, I have very little knowledge on it.
Okay. The same person has asked also, can you tell about IGCT switches and its usage over IGBT?
Again, I'm not aware of IGCT switches. I have seen IGBT. I do not know what is IGCT. IGBT MOSFETs. These are all silicon devices. IGBTs are generally used when the power levels are quite high than MOSFETs. MOSFETs are employed at medium power levels where you can switch at much higher frequencies. IGBTs, the silicon-based IGBTs, they are switching frequencies limited to 20 kilohertz. They cannot go much beyond that. But nowadays we have silicon carbide devices, that is wide band gap devices, and gallium nitride devices. These are now extensively being used for DC-DC converter applications.
Okay. Next question is, in a grid connected solar PV system, it is seen that the current harmonics is high in the solar PV PCC when the sunshine is high more than 90% and the system load is less than 10%. Why this happens?
Yeah, that's because the system is mainly designed for the rated application. So whenever the load increases, you would definitely get that. And again, I feel that whenever we design the control systems for such cases, we generally try to do it at rated conditions or very close to rated conditions. So at low rated conditions, we would definitely have the current harmonics. And even the hardware limitations also introduces the current harmonics. This is what I feel. And that is acceptable because harmonics at low load is acceptable in practical conditions.
There are 2-3 questions more. I hope it's fine if we
Yeah, it's
continue.
fine. Madam, I also want to show some simulations. So I hope I would have time for that.
Okay. Or maybe we can see the simulation and then carry on.
Okay, then that's fine. That's absolutely fine. I'll try. I'll share my screen. 1 minute.
Yeah.
I'll just take out my. This is. I mean, it's too difficult for me to explain all the parts, but I'll just give you again. The idea is just to show some of this thing. Please let me know if my screen is visible, madam.
Yeah, it's coming up. Yes, now we can see the PDF doc.
Okay, yeah, this is a PDF doc. This is actually a script file, a MATLAB script file. So where I tried to write a script file to how to get the transfer functions for the very DC-DC converters. What I want to convey to the participants here is you need not do these operations manually. It can be done easily in MATLAB. Where I have seen, as seen in the screen, but I'll make it in full screen mode. Yeah, as seen in the screen, you can define various parameters. You can define the matrices, okay, and write the transfer functions for the boost. Okay, so even for the higher order converters like Sepik, Chok, Leo converters, you need not do it in manually, and it can be done in MATLAB. It's quite straightforward. Now, those who do not have MATLAB, you can use Octave, which is an open source software, where you can actually write these and see design the compensators using this transfer function. So that was the intention for showing that. Now, next, coming to the simulation. Okay, so here I will start with the voltage control for the boost converter. I have actually written a script file, which I'm not going to discuss it in detail. I'll discuss the simulation part carefully. So I hope my screen is visible. So this is our DC-DC converter. This is a boost, which I can show you inside. Okay, it may not be visible clearly, but at least you get an idea here. Okay, so this is the output voltage. So you can see this is implemented in digital domain. So you can see that the reference I have set as 375, output voltage V0. Okay. So I have the voltage controller and the pulse generator. So the voltage controller you can see is here. Okay, so if I double click each, I have actually written a script to get the value for A, WZ, and WP. So this is actually a type 3 compensator which is employed. So if you see carefully here, this is what it looks like. It can be done very easily. Even those who are not in power electronics domain, you can start off trying to simulate this converter. I'll not run the simulation because of the lack of time, and it doesn't convey also much at this stage. So I just wanted to show you this. I'll go ahead with the next one, where this is the current control done in digital domain. Okay. Okay. Now this is the reference, the actual current. And this is the current controller, which I've done it in a digital domain. So what I've done is I have converted the integrator part, that is A by S in discrete domain. And this is how it looks like. Only thing we need to be careful here is when I select the sampling time, it should be equal to the sampling time of the ADC. Okay. So with that, you can actually build this and check how your performance is even in discrete domain. So see, this is the lead part of the compensator, which I've done it in discrete domain. How do I get these values of K? Well, that comes from the bilinear transformation. So you design the controller in S domain, converted it into the discrete domain, and you will get it what has to be done. So what I want to convey the viewers here is that when you design the compensator, when you're trying to follow the first approach, that is the analog design approach, you design the controller in S domain, run the simulation in S domain, see if it works fine. Then convert it into digital domain, run the simulation in discrete domain, see if it works fine. I would say if it works in discrete domain, fine. 90% in actual hardware, it would work. This is from my personal experience. Sometimes in 10% of the cases, you may have to tune it here and there. This is how we do it. Maybe there is much better approach. This is one approach which I followed. Okay, I will just show you the PFC converter as well. I think I have that. Okay. Okay, so this is something PFC converter where I told you you have a AC source, you have a bridge converter. It has a very good practical implications. All the LED drive systems, you have such kind of systems. So here again, I have used interleaved boost. You can also have a boost converter, simple boost converter, and just trying to have the entire control loop. Again, I'm not showing it, but what I can say is before you go ahead with the actual practical implementations, you or your student, you can ask your students to implement them in MATLAB in a systematic way where we have designed the controller in a more systematic way. So I have used the K-factor approach for designing the controller here. Okay. Of course, this kind of systems also require PLL. I'm not discussed PLL. See, I have a PLL here. I've not discussed PLL, but PLL also is, you can also study that. And even the controller design in a PLL is in a similar fashion, where all these methods I have used is called loop shaping method. So even in PLL case, you can use loop shaping for designing the compensators. Okay. So that's it from my side, madam. Then we can go ahead with the remaining. Is there any other question related to simulations? I can show some of them. Otherwise, we can go with the Q&A session.
For the simulation side, so far, I think no one had asked. And a few of the questions remaining is how the PWM and sampling delays can be incorporated in the modeling, and how will it affect the stability?
Yes, the sampling, yeah, I do not know the theory in detail, but one thing we know from the conventional control is that having the sampling frequency as high as possible is better. Okay. So the thumb rule that we generally use is that the sampling frequency should be greater than or equal to switching frequency. That is this thing. Now in the modeling, we can see in MATLAB simulation, I've just shown you here, where we can incorporate that sampling in that Z block, Z inverse block, and run the simulation with that sampling time period.
Okay. I think this also you have mentioned, but if you have anything further to add, the question is, can you suggest the best controller while dealing with voltage or current control?
I have seen, yeah, I've seen it always in industry with this traditional linear controller is more than enough, except for the boost converter or converters with RHP zeros, where we can use some sort of a nonlinear control. Otherwise, I've always found linear control to be extensively used in industry. But yes, nowadays in the academic side, we have too many nonlinear controls like sliding mode control, which is being implemented. But it would be incorporated in industry if we can convey it very clearly the advantages of these. Right now, what I find is that has not been conveyed it or may not be there. So there are that's what I can say from my side.
Last question, like how you can relate the switching frequency with that of the closed loop bandwidth?
Yeah, that's what I have explained, that the closed loop bandwidth should be as high as possible to have a lower settling time, but not in the order of switching frequency, then because then it would have the controller would affect the dynamics of the plant. So we could always have below the switching frequency, and the thumb rule is always have 1/5 or 1/10 the switching frequency.
Okay. And last question is like, can you share some good reference material for simulation of controllers for DC-DC converters in MATLAB or Simulink?
Yeah, there is. I'm not sure if there are any reference where they discuss. There is one book by my teacher, Professor M.B. Patil, where he discussed simulation of power electronic converters. He has written a book. He's not from power electronics domain. He's mainly from, I think, from the microelectronics domain. But he has a book, Professor M.B. Patil, The Control of Power Electronic Circuits. But there he never encourages MATLAB. MATLAB, I mean, he in IIT Bombay, they have developed their own software. I'm not remembering it, which is an open source software. So he encourages that, and he promotes open source software. But that book mainly discusses how do you simulate power electronic or how do you simulate power electronic converters, and how can you simulate it such that it reflects the actual system. So that is a very good textbook. He has done it. There are numerous textbooks on simulation of power electronic converters. So those who are interested can Google search that, simulation of power electronic converters.
Okay. And is there any method to export an inverter control developed in Simulink to ETAP for control and inverter in the SLD done there?
Okay, I have not used ETAP that much, so I'm not sure. Anyway, there could be a method. That is again, I'm not sure how ETAP helps.
Yes.
Yeah.
Yeah. And so I think it's time that we can conclude. And I really would like to thank Dr. Prajof and through by organizing this event, I was able to come in contact with you, and
Yeah.
it's great to get in coordinating with you. And the topic for today was, I think, it dealt most of the things that the power electronics side engineer should look into the control aspects, and also for controllers like us. We hardly know how certain system behaves, and that also you have given us an insight. So while we design what are the points we have to take in note. Thank
Yes.
you, Dr. Prajof. Thanks a lot, and
Thank you,
hope we
ma'am.
can
Thank you. Yeah, yeah.
get in touch in future also.
Sure, sure.
Yeah.
Thank you. But before I close, I would also say that even the faculties who are another domain, there is a good scope, a research scope in power electronics. Especially, I see some of my lab mates who are working in IIT. I did have lab mates from control domain working in power electronic systems. So what I see is control domain people do have the knowledge, but some of the challenges in power electronics, it can be easily learned. So in fact, I strongly believe the person with control background can contribute a lot to the power electronic systems.
Yeah. So I think we have to start working together, control
Yeah.
power electronics, power system, everyone together.
Yes, that's true. Today it's an interdisciplinary domain
Yeah.
which needs a good understanding of all the aspects. Yeah.
So I take this opportunity on behalf of the Department of Electrical Engineering, Rajagiri, to thank all the presenters and all the participants who have stayed for the 5-day FDP. And I hope that we were able to give what we had planned. And surely there were feedbacks which will we consider in our future FDPs. And before we conclude, I have just one small uh, thing to share. Like, we had few question answer sessions during our WhatsApp, in our WhatsApp group, and I had said that whoever participates well over there, I would we will have some appreciation for them. And so I'll just try to share my screen now, and just let me know if it's visible. Is it visible now?
Yeah,
Yes, ma'am.
it's visible.
Yep. So we have a few participants who were actively participating with us. So I would like to extend the appreciation to Ms. Sanjana Salim of CUSAT for participating and for answering most of the quizzes we had. Then we had Mr. Riju Rajan from Providence College of Engineering, who also gave in really good explanations for a few of the questions and really made us think. Then we had Mr. Nikhil, who kept in communication with us during when the questions were posted. Uh, and also I would like to thank Ms. Jayshree PR from Amrita Vishwavidam for participating in the quizzes. So I definitely extend my thanks to all the participants who were actively participating in the quizzes. And these are just few appreciation, just as we did some event. And so I thank all the participants once again, and hope we can meet in any future events, virtually or face to face. And I would also like to show one of the upcoming events in our department, which is going to be started in the next week. If interested, you can share. This is especially for the students, so you can share with your students and researchers. It's on EV. It's a paid course, uh, and these are the details. So if anyone is interested, they can join. Thank you once again, and have a great evening.